Hi there. Welcome to Bioconductor 2021 in this package demo session on infinitely scalable data analysis in R with TileDB. We're going to start the talk soon, but first a few announcements. If you have questions for the speakers, please enter them in the Q&A tab. You'll find that on the right of your screen. And you also have the ability to upvote questions to the speaker. If you see a question pop up and you're like, yeah, that's me too, feel free to upvote rather than filling the Q&A tab with more copies of the same question. And if you'd like to ask your question live, please use the raise hand feature and a moderator can bring you on stage. Also, at the bottom of your screen, there's a bunch of emoticons available to give feedback to the speaker as well. So if for some reason you're feeling like you really think something's cool, there's even there's a cool face. So I've seen that one a few times today. That's pretty fun. And if for some reason you have to leave early, there's a video of the session will be available in a couple of hours after the session has completed. So without further ado, please allow me to introduce our speakers, Aaron Wallen and Dirk Eddelbuettel. Dirk is going to start, and I'm going to get out of your way. Thanks, guys.
Thanks for the introduction, Mark, and I hope that everybody can now see my screen. So a warm welcome and thanks for the intro from Aaron and myself. We're both engineers over at TileDB, where we work on a data backend system that we're going to talk about in this demo. We've been working quite diligently to provide R bindings to these, and Aaron in particular has worked quite a bit on bioinformatic applications that the majority of this presentation will be about. I'll just start out a little bit with some generalities. We have been giving a slightly longer version of this talk with slightly less focus on bioinformatics at the recent UseR conference, and a longer format set of slides as well as examples and code is available from that if you want that. So I'll briefly say something about TileDB, the company and the system, and then feature a couple of highlights, namely dense and sparse arrays, the fact that the full API is wrapped, and really briefly access to cloud, in particular AWS S3's bucket format, and returning data in Arrow format before I turn it over to Aaron, who will then show you a couple of bioinformatic genomic applications before we wrap up and show you some further references. If there are any questions, because there's two of us, if you put them in the chat, Aaron will be able to signal to me and we can take questions live or otherwise at the end in the final 15 minutes. So really, what's TileDB? TileDB makes a bold claim and says, we're offering a universal data management system, and the magic behind it is provided by multidimensional arrays, either dense or sparse. And I'll come back to that in just a second. It's serverless, so it's different from a relational database or other system where you connect to a port, send commands. It's a file system, if you wish. So it is a really, to take a somewhat matching but still bad analogy, it's like SQLite, but at global scale. There's just a layer that you use provided by an API to access storage in a particular format. And because of that universal API, that bindings to different applications and user languages can be provided for, the access is always the same because it always goes through the same code path. So you don't have this pain that you need to normalize and QA check that the data that you've written in one system under this umbrella comes back the same way. It all goes through the same. So what we're talking about today mostly is the R package, but there's also a very active user community using Python as well as other languages. The slide on the left comes from a recent presentation of ours and illustrates a little what happens. So at the bottom, you have different representation layers on which we can place our storage. Any of the three large cloud providers, AWS, Google Cloud, or Azure, as well as Minio providing S3 maybe locally, distributed file systems like Lustre, as well as Hadoop. And they all go into what we call TileDB Embedded, an MIT licensed open source C++ based library that you link against. And from there, you can get to all the things in light blue at the top: Python, R, Java, C++, Go, as well as applications such as Spark, as well as MariaDB and or domain-specific applications like GDAL and PDAL, and then pandas. The graphic is a little misleading in the sense that you don't actually need TileDB Cloud to get to TileDB Embedded, but it's a little hard to visualize that. The pass-through from the data storage via the embedded library to the applications can happen with or without TileDB Cloud. But TileDB Cloud, a software as a service layer, allows you additional management aspects to that. We won't be talking so much about that today, but there's more information about it on our website. So key features of TileDB really is it's native and built for the cloud. So we deal really well with AWS and AWS scaled size, as well as the other cloud systems. It's really just our one library and nothing else. And by virtue of relying on the cloud systems, we get their massive bandwidth and essentially unlimited, indefinitely scalable storage. Because it's cloud native, it is set up in such a way that both reads and writes are fully independent and parallelizable. All chunks are immutable. That also makes them thread and process safe. And indexing can be done in on multiple dimensions or attributes, and we'll have examples for that. And in general, sort of one good chunk to take away from this is that query times should really just grow with the size of the result of your query rather than the size of the stored data. We, for the longer tutorial, had provided an example package. Somewhat informally, it sits under my handle at GitHub. So the examples that we'll be showing as well, I think, as the examples that Aaron had provided are in that repo, so you can get them from there if you want to rerun them. And these standard R lines show you how to install that, but I presume almost everybody is familiar with that. And then once you have it installed, a minimal introductory example is shown on this slide. You may have to do install.packages TileDB. That should work on all major platforms from CRAN. You just then call library TileDB. And for one example that we like to use here, I'm using the Palmer Penguins. And just switch to a Scratch directory for the purposes of this example, because I'm not qualifying the directory that I'm writing the data to. And then converting an R object into a TileDB array can be as easy as calling from data frame, taking a data frame or data frame alike object in R that can be cast to a data frame and writes it to an array with the given path. We generally refer to them as URIs because they can be local or remote. This chooses a couple of defaults, examines the data structure, and chooses an appropriate representation as well as defaults. Compression is on and sort of things like that. The other way back uses generally a helper function TileDBArray, where we give the URI of the array that we want to access, here penguins that we've just written, as well as a number of qualifying arguments that govern how the data comes back. By default, because the data really is stored columnar, if you don't specify anything else, you will just get a list of columns, which is fine, but a little unwieldy. So if you want a data frame, you have to say as data frame. And the next argument shown here, extended, is just a toggle for yes or no, that if you hadn't given an explicit index column, as we hadn't in the line above where we write, then row numbers are added as an implicit index, and extended basically just says hide the implicit index. And when you then show R, you get basically the same data set back. And that would just look this way. If we do SDR on it, a data frame comes back 344 times 8, which is the data going in. And as you see on a glimpse immediately, thanks to the highlighting provided, we cover ints, we cover doubles, we cover characters, we cover present values as well as missing values. So most of the things that an R user is concerned with are taken care of. When one goes into a little bit more detail beyond the introductory example, one choice to make is whether one wants dense or sparse arrays. That choice, once made for an array, is not reversible. So you've picked one or the other. And the trade-off are essentially what you would expect. Dense can be a bit more powerful at the expense of being less general. Dense arrays need to have the same indices in all dimensions, homogeneous, we call that. Sparse can be heterogeneous, and sparse generally gives a bit more flexibility, but may incur a slightly higher cost in reading, as you would expect. You can have one or multiple indices on sparse arrays. There are different options, tuning parameters, and what have you. So there's more documentation and a lot on the website, but that gets us too far from a short overview, so I won't be going to that. So let's start then with dense arrays, where everything started. I've borrowed a graph here from our website showing a two-dimensional dense array, and dense arrays really have the main characteristic that every cell has to be present. They have to be dense. An individual cell could actually contain multiple values. So it doesn't have to be a 2x2 array or matrix in the R sense with a single cell. It could be what we now sometimes do with data frames or tables or whatever, where there's list columns. So every cell could contain multiple things. So you could have an array where one cell is a triplet for RGB values to represent imagery, say. There can be labels and there can be metadata. And in general, you will use dense arrays when you have such dense data and want it in highest performance. And we had quite a bit of feedback already back from users of the DelayedArray package in Bioconductor about use cases for dense arrays. I mentioned at the intro that the TileDBArray package wraps the underlying API directly, and the underlying API then has calls like these functions that we see here. Where in the middle of the screen, for example, you see TileDBDim to set a dimension explicitly. So here we would say, okay, we want to dimension rows going from 1 to 4 with a range of 4 of type int32 really explicitly. That's an alternative to doing it with from data frame. So here we're setting 2 rows and calls, just as in the chart on the previous slide. And then the actual attributes here is a single column, also int32 with the name A. And domain goes into the call for TileDBArray schema, creating a schema, and given a schema, as well as a place where to write it, a path, a URI, creates an array, which at that point is empty and can then be written to. And you just write to such an array as you see on this slide in the last line by assigning via the square brackets. Here, data is a commensurate data structure for this two-dimensional 4x4 array. So it's dense, so we have every cell present. It's a little boring because you just go from 1 to 16, but that would be a minimal if complete example. One thing that's convenient is, of course, that we can cast them back on the way out. And a few of the features on this slide are actually net benefit from feedback I got from Bioconductor users, because there are use cases where folks want matrices, two-dimensional arrays actually coming back as an R matrix objects, and or more than 2 dimensions array. So all this works. And as you can see, we're just setting different attributes in the call to TileDBArray. We had already seen, or it mentioned the first line, that if we don't say anything else, we will just get a list of the columns. Or we can say we want it as a data frame, which once we have lists, just internally really does the as data frame call. Or for suitable dimensions and types, it can come back as a matrix. That, of course, requires 2D, as well as an array for any commensurate numbers. So if you have 5-dimensional arrays, you can store them that way and they come back. R has some difficulty displaying that concisely, but you can represent them. And data frames, just as we had it in the intro example, can also go in a dense array. We then just have dense column vectors. So here again, it's the penguins example, but here now I take penguins raw rather than the digested data, write it out to an array and read it back into the new DF. And then this comes back as 344 times 17 because the raw one is wider than the condensed or polished penguins dataset. But sparse arrays are maybe of interest for another set of applications, and they are more general. Sparse arrays, just like sparse matrices, most of you will be familiar with this, can have sparsity, and so not all cells have to be present. We have no golden rules about what level of sparsity you need at a minimum maximum. It's really sort of up to you. The dimensions can be heterogeneous. That's something that we changed about 6 or 8 months ago with TileDB 2.0. So it can be strings and numbers or dates and numbers, any combinations. Metadata, again, is allowed. Cells can have multiple values. And as shown on the bottom left, duplicate values are also allowed. So a dimension object does not have to be unique. Here's then an example using actual R sparse matrices from the matrix package. That's just an example I'd used somewhere else. We're just sampling out a matrix and then making that an DGT object that's shown on the next page. And just how we have from data frames, there's also a from sparse matrix constructor, and conversely, to go the other way, to sparse matrix. And when you run that, it comes back after the read from TileDB and looks exactly the same way as the object would have looked had you taken it directly from DGT matrix. So this one has, I think it was 15 out of 160 cells filled. Sparse arrays also work really well for data frames because of the indexing. So here is a reworked penguins example where, contrary to the previous example, I now say sparse equal true. I give two explicit indices, the species and the year. And that bears stressing another point. We had said the indices can be heterogeneous. And when you have textual indices, string values or character vectors in R speak, we already have a domain that is basically from null to null, because you don't have a meaningful minimal or maximum value for characters. For numbers, however, you have to, or you may want to give an explicit min and max value, because if you do not, then the min and max for that domain are taken from the observed data in the object that you're presenting. And that makes writing, appending, say, outside of that range harder. The Penguins data set, if you know it, I think has observations from 3 years, 2007, 8, and 9, if I'm not mistaken. And here, to stress this point, I say explicitly, no. I want a year range from 2000 to 2021, allowing me to put other additional observations in to grow the data set. And that's really all that takes here. Tile domain is a list that goes over possible index vectors. Here I have two index vector species in year, and for one of the two, I give the domain explicitly. And when you do that, then you can read back again with TileDBArray, just as we had done on dense arrays. But now you have an additional opportunity to slice. So here I'm saying I would like a subset back that is only 2 of the 3 possible years and only 1 of the possible species. Because we want, anyway, so we have a specific way of selecting these constraints to be really sure that the evaluation is lazy and pushed to the data. So we're basically sending a list with matrices for each of the possible dimensions, and each row in the matrix can be a min and max value. So here we're basically saying an interval from 2007 to 2008, brackets included, and a string interval from Gen 2 to Gen 2, meaning basically equality, because they're greater than and less than, hence from both sides. And those are the dimension columns that we sort over. A very interesting and more recent feature is that we also now allow selection on the actual attributes. Remember that the Penguins raw that we wrote here was 344 times 17, and we had given 2 columns as indices, leaving 15 others. But here, for example, we could now say, give us all the birds back that have a body mass in grams that is greater or equal to 6,000. If you write that by hand, as in the first line, directly wrapping the underlying API, it's a little terse, but basically you set up a query condition object, or you initialize a query condition object and then assign it to the query condition attribute of the query. That's standard S4 mechanics behind it, and then X is endowed with that attribute, and the retrieval via the square brackets will respect that. We've also wrote a little helper that makes it easier to write one or multiple nested such condition, and that's pass query condition. So just as we said above, body mass in grams greater than 6,000, you can just write it as an R expression, just like a formula, no quoting, what have you. And you can also combine that over multiple conditions. So here we're selecting one more. We're saying body mass greater than 6,000 and only male penguins. The work on string columns is pretty new. That's not actually yet in the CRAN version, but it's on GitHub. And one final last thing is if you want to slice columns rather than rows, you say which attributes do you want back. So this particular use case on this slide would only return 2 of the 50 non-index columns. And then lastly, writing in batches is supported, as I've shown, by making the index ranges large enough to accommodate future writes. So you can, of course, index ints or doubles with int min, int max, double min, double max, and then there's absolutely no limits, or you can set particular ranges that may be application specific. But when you do that, then you can write different independent chunks to the data set, and they'll get retrieved properly. There's more management there that you can combine some of these chunks and lots of other stuff that we don't really have time for. Let me just focus again once more on the 2 in and out helper functions. So from data frame, as I've shown, is the high-level array writer. We try to put a little bit of logic into this, so it can pick indices for you, or you can give them to it. It can write dense, it can write sparse. It defaults to using one of the many available filters. We use Z standard for compression because it has a good balance between performance and compression ratio, but there are other ones that you can set explicitly. You can set particular attributes and parameters explicitly, and it supports append mode by setting the domains wide enough. And I guess I should have taken off the last line because that was in reference to the longer tutorial. And then the other way around, TileDBArray, the reader, can read dense or sparse, gets lists back as well as data frame metrics and arrays, and can select by rows as well as by columns. And that's sort of what I had in a really fast overview of the basics of arrays, and then just 2 more features that are worth stressing. Everything that I've just shown you worked on local directories, essentially. And wherever we drop the local directory, we can equally well drop an S3 bucket. So you just replace the URI with something S3://, and provided you have your environment variable set, either in your shell or in the configuration object for TileDB that's shown in the docs as well, it just seamlessly reads and writes with no extra layers. So you have immediate cloud access, which is pretty nice. And that just takes all URI accesses from read and write. So here is a working example with a data set that we made public. So if you have TileDB installed, you can run that line, and indeed, plop, you get your 344 rows of penguins back from a public bucket of ours. And then lastly, Arrow is becoming quite popular as an in-memory format, for example, up from Feather file formats. Arrow has a no-linking C interface, sort of void pointer, that we can hook on. It looks a little tricky, but this slide does it, but I don't want to go over it because that would basically take a minute. We have to assign 2 pointers, and there's an on-exit to release them later. And then it just uses that trick. And when you do that, your TileDB data is actually represented as an Arrow vector here, just a boring 3-element int8 vector. And that's pretty much what I had, and I will stop sharing now. And because I took just about as much time as I thought I would take, maybe it's best if we just let Aaron continue and we take questions at the end. So Aaron, over to you.
Cool, thanks, Dirk. Let me switch over to my screen here. Are you guys, can you see that? Can, good, great. Okay, so like Dirk mentioned, I'm going to cover a few different genomics use cases for TileDB now that you've seen sort of an intro about the format and the R package. But I wanted to start off real quick by talking a little bit about TileDB's roots, since they are actually in genomic data management, which I think would be of interest to this audience. So the underlying tech was originally developed by Stavros, who's our CEO, while he was at Intel Health Labs and working with the Bro to solve the scalability issues they were facing when generating multi-sample VCFs for the increasingly large populations they were working with at the time. And the solution they came up with was called Genomicsdb. And if you use GATK, you might have heard of it because it's still part of the GATK pipeline today. So that's where it all started. And of course, TileDB has evolved quite a bit since then, transformed into the general purpose storage engine it is today. But it's still a really excellent solution for managing this type of genomic data. And in fact, within the genomics domain, we have primarily focused on developing our solution for fast, scalable variant call data management. So this is implemented in an application that's appropriately named TileDB VCF. It's a free and open source tool. And we have customers that use it to store VCFs for hundreds of thousands of samples, and it works really well for them. I'm not going to show any code here for this because while we do provide several different APIs for TileDB VCF, R is unfortunately not one of them. But we are a very customer-driven company, so please get in touch if that's something you'd be interested in seeing. I personally think that would be very cool to add. In terms of interfaces that are available for R, I wanted to mention the TileDBArray package, which is a bioconductor package developed by Lun. So this allows you to use TileDB as a backend for the amazing DelayedArray framework. So if you're already using DelayedArray or any of its many dependencies, this is a really great way to try out TileDB using a familiar interface. And I will also mention that single cell data management is something we're starting to focus on more internally. Like I said, we've primarily focused a lot on population genomics, but single cell is a use case we are very interested in pursuing. So this is something we plan on contributing to in the future. But today I'm going to focus on the base R package like Dirk, and demonstrate how you can use it to handle several different genomics-related use cases. So I'm really sort of stressing the flexibility of TileDB here. So we're going to look at a few different data types and then different strategies for storing the data in a way that facilitates efficient slicing for typical query patterns. So I'm going to start with genomic annotation data. Specifically the kind of information you get about genomic features from Ensemble and their GTF or GFF files. And this is a use case that sprung up with a customer that's rebuilding a clinical genomics database with lots of different annotation tables and the UI for retrieving variants based on gene queries. So we needed to be able to convert those gene IDs into genomic regions. And they were specifically working with Ensemble gene IDs. So I used Annotation Hub to retrieve the Ensemble GTF file with the most recent annotation data, converted that to a data frame, which looks like this, and ingested this into a sparse TileDB array with a single dimension for the gene IDs. So this is essentially the index, and that's what allows us to quickly slice the annotations for a particular gene, even when the data is stored remotely. And I put copies of these arrays onto a publicly readable bucket. It's on S3. So anyone here can experiment with these data sets yourself if you like. Just keep in mind that for the demo queries I'm going to show, I'm using the development version of TileDBR on GitHub because it includes some of those newer query parsing features that Dirk mentioned. So I'm going to switch over to R now and run through a few of these example queries. So I'm just going to load the TileDB package. I'm using the Tibble package here just to get nicer output for the query results. And the Ensemble annotation array is available here. So I just need to load this array and indicate I want the results returned as a data frame. And then to query it, it's as easy as just using a square bracket notation. Just pass along the gene ID, just like you would use a row name for a data frame or a matrix. And you can see this returned 122 rows because it's returning results for basically all of the different annotation levels that are available. So gene, transcripts, exons, etc. So anything associated with that gene ID. If we were interested in just the transcripts associated with this gene, then we can take advantage of TileDB support for attribute filters, which are the query conditions Dirk mentioned earlier. So I'm just adding a query condition here that says filter the results for rows where type equals transcript, adding that to the array. And now that condition is going to be applied to this array for all subsequent queries until I either close the array or clear that condition. And then when I rerun the query, it applies that filter. So now we get fewer rows. We just get 7. And we can refine this further by only retrieving the attribute columns we're interested in. So in this case, I only need the transcript IDs and locations. So I'm going to update the array object again to specify those attribute names. And now when I rerun the query, those are the only columns returned. And so the beauty of working with a columnar format like TileDB is that it's only going to touch the files containing the requested attributes. So this additional selectivity can really improve performance, especially when you're working with remote data. So I think you can see how something like this is convenient for interactive analyses because we can retrieve just the data we're interested in. You don't have to download the entire annotation file. So as long as everything's in a bucket that's accessible by everyone on your team, you can all be working with the same data simultaneously. So I am going to switch over to our next example, which is the two-dimensional case. Oh, I think I hit the wrong button. Sorry about that. Is that up again, Dirk?
It's coming. Now it's back. Yep.
Okay, great. So let me update. Yeah. So the next example is probably the most obvious use case for the bioconductor community, and that is a two-dimensional matrix. So anything like a gene by sample count matrix or anything you might normally stick into the assay slot of a summarized experiment object. And these types of structures are really a good fit for TileDB because you have the option to store them as dense or sparse arrays depending on the data. So for this example, we used RNA-seq data generated by the GTEx project. And this includes measurements for 56,000 genes across 17,000 samples. And we were working on a dashboard prototype that would allow users to basically visualize the expression of a particular gene across different tissue types assayed by GTEx. So here's a glimpse of what the raw data looks like. There are no missing values, but about 50% of the measurements are 0. So I ingested this data set into a sparse array to avoid having to store all of them. And I used a 2D array with 2 dimensions, one for gene ID, one for sample. So you can think of it as sort of a long format table like this. And the only non-dimension attribute here is the TPM column with the expression values. So let's load up this array, which is also stored on S3 and is readable by everyone at the conference. And again, we can slice out a particular gene by just passing the gene ID. So that's going to retrieve all the non-empty expression values here across all of the samples. And in this case, that gives us back just over 3,100 rows. And so the second part of this use case is we wanted to be able to group that expression data by tissue type. So we also need access to the sample metadata. And of course, we can use TileDB for this. It's actually a really similar use case to the gene annotations. So I just downloaded the sample attribute file that GText provides and literally just used TileDBArrays from data frame function, like Dirk showed you, to create an array with all of the available sample metadata. There's quite a bit here, but all I need is the SMTS column, which contains the tissue type labels. So I'm specifying that here when I open the array. And I wanted to apply a filter because I want to pull out the sample IDs for a particular tissue type. So I'm using a query condition that pulls out just the results or just the records where SMTS, which I forget what that stands for, but it's something sample tissue type equals skin. So we can apply those select and slicing filters to the actual array when we create it. And then when we perform the query, they're automatically applied. So you can see we're only getting that single SMTS column and only getting the rows that equal skin. And I'm using these results below just to perform one additional query with the RNA-seq data, basically just to show we can slice this large two-dimensional array across both dimensions, the gene dimension and the sample dimension, which we're now limiting to just those skin type samples. So we do that by adding a range selection here. So it's just a list. We have two elements, one for the gene ID and one for the sample dimension. And then running that query, we should get many fewer results. So now these are just the GText RNA-seq values for those skin samples. So that is our two-dimensional case. We are going to go through one more example. So I'm showing all these examples live, but if you look at the slides, all of the code and the results are there if you want to look them over later. Okay, so the last case, slightly more complex, but it's going to allow us to index data by the genomic position. So we're able to slice using genomic ranges. And I'm referring to genomic ranges in lowercase letters here. Unfortunately, there's no integration with the Bioconductor package, but again, if that's something anyone's interested in, please get in touch. Okay, so our use case was creating a database of summary statistics from a large number of genome-wide association studies. And we wanted the data set to be accessible by the ID of the trait and a genomic location. So for the demo, we downloaded results for 500 phenotypes that were analyzed by the UK Biobank. So each of those original GWAS result files contain about 10 million rows and include columns with your typical GWAS summary stats, along with a variant identifier column. So to store all of this data in a way that allows for efficient slicing across both the phenotype and genomic region, we're going to use a three-dimensional array. So 2 dimensions are used to index the genomic location of the variants. So they're stored by their chromosome and their chromosomal position. And so with those dimensions, we can perform queries for specific locations and retrieve the corresponding cell. Then inside each cell, we have the values from each of the different columns in those results files. To add the additional GWAS results, we'll add one more dimension that indexes the name of the analyzed trait. So this is sort of a representation of that schema. For the actual array, we used phenotype as our first dimension because we were going to be querying for GWAS specific results. So selecting a particular trait would automatically filter out the vast majority of cells. So then TileDB can quickly zero in on the relevant slice of the array. So this is an example of a decision you want to kind of think carefully about if you're creating large arrays, because the ordering of the dimension can have implications for performance. So in this case, it made sense to go phenotype first because we were almost always going to include phenotype IDs in the queries. Okay, so let's look at a few query examples with that data set. This array is also publicly accessible. It's, I don't remember exactly how large. It's several gigabytes. So I did not make a copy of it from the UseR conference, but this bucket is publicly accessible. So I'm going to open up the array. I'm going to pick just a subset of the columns that we're interested in. And we could use square bracket indexing with this array, but we would just be limited to the first two dimensions. So in this case, phenotype and chromosome. I'm not going to run this live because this returns like 300,000 rows, but it does work fine. If you want to include the third dimension in the query, then you need to switch to the selected ranges syntax we've seen before. So again, we have a list inside of which we have one element for each of the three dimensions. So phenotype, chromosome, and now we're adding this positional query to pull out any variance between 5 and 6 million megabases on chromosome 20. So we can add that, run our query, and it should pull back all of the results for that. Yeah, so that's the slice of the array that matches the criteria that we have imposed. And so that was my final example for today. Oh, and good, because I see time is low. So I will wrap up very quickly. So yeah, this is sort of our overview slide of TileDB itself. You know, as we mentioned, both the storage engine and the format are open source. We want to underscore that because, of course, you know, this is a biomedical research conference. So you know, you need to know if you're going to use TileDB to store your data. There's never any risk of, you know, being locked into a particular vendor or anything, because everything's free and open source. You will always have the ability to get your data out just as easily as you put it in. Of course, you know, Dirk mentioned we're fully cloud native. So any array you create locally, you can also store remotely in the cloud. This provides, you know, limitless scalability. So we're only bound basically by the bandwidth limitations or storage limitations of, you know, these three rather large companies where that is not much of a consideration to worry about. I think Dirk covered the R package very well. It's available on CRAN. It has a high-level interface that's meant to be very user-friendly for R users, but it also provides full access to TileDB's low-level API for more advanced use cases. docs.tiledb.com is where you can find all of our documentation. There's lots of examples and code snippets and tutorials to get you started. And yeah, please do get in touch if you have any questions, if you have a feature request or want to discuss a use case with us. I'll leave this up so you can explore the myriad contact options that are available. And I also want to mention we are hiring. And in particular, we're looking for some C++ expertise from anyone who has experience working with genomic data. So please drop me a line if that's of interest to you. Otherwise, I'll stop there and we can take any questions you have. With our remaining minute before the session ends.
There are 3 questions in the Q&A panel. Oh, now for the others 4.
There's a few on the channel.
Can you see them? I can read them to you.
So Dirk, did you see the question?
I can read them, and maybe I had a chance to look at them. there's definitely one or two that I'll pass on to Aaron. The first one came in by Joshua, and that's a good one. And I have been trying to scratch my head off about an existing example, and I can't think of one, but that should be possible because dimensions and attributes internally are not different. And as we allow multiple cells, you should have multiple cells in multiple values per cell also in the dimension vector. I'm a bit hard pressed about how I would couch selection queries then, but that should be possible, but we should probably cook up a particular example. So I would invite you to get in touch with us with a small mock example, and then we see. But there's no fundamental limitation to have that. The next one, I think I'll just the next one that came, I'll pass on to Aaron, because that was specifically about how it compares to variant Spark and Spark comparison. So I actually don't work with Spark, but I think we should run circles around it, but I don't know this particular product. Maybe you do?
Yeah, we have people at the company with more expertise in Spark than I do. Let's say the most exposure I've had to Spark is through TileDB VCF, since we offer Spark integration. It's very hard to make these kinds of direct comparisons because there are so many variables to consider. So usually when customers get in touch and ask about benchmarks, what we do is we kind of have discussions with them about, what are the specific queries you're interested in? What are the operations you're trying to perform? And then take it from there, try to set up a demo so we can make an apples to apples comparison as closely as possible. Otherwise, it's hard to kind of just, shoot off benchmarks because there are so many different things to consider. Spark is great, and that's why we offer integrations with TileDB Core and some of our integrations like TileDB VCF.
Yeah. And there's a connector via Presto, just how we have a connector via MariaDB to SQL. So if you have existing Spark pipelines, you can use it. But again, from 30,000 feet as a non-Spark user, I'd often seen it motivated as a mechanism to make really large data fly. And what we just shown live, Aaron, during the presentation is if you have the data actually in cloud storage, you don't need the Spark machinery because you get that scaling aspect provided over on the other side, and you save, all the node startup and other headaches that maybe there with Spark. But I'm not a person there really to make a comparison. So, but I would think we should be competitive. The next question is clearly an Aaron question, so I'll duck and let him take that about Annotation Hub and Experiment Hub.
Yeah, so I think it would certainly be possible to add TileDB arrays to Annotation Hub. I'll focus on that because I haven't used Experiment Hub as much. But the use case is a little different because Annotation Hub is for downloading the entire files, right? So in my example, I was using Ensemble annotation. So Annotation Hub makes it really, really easy to download the full GTF file to your local machine and get access to it that way. If you store that data in TileDBArray, there's no reason to download the entire file because you can slice it live from your local machine and just access the parts of the data you want to. So that's the difference. It's in sort of an analysis ready format. So you can just load up the array and start working with it as though it were local, even though it's all stored in the cloud.
And I may try to take a shot at the next one by Lambda, who basically says, nice try, guys, but that didn't look like R. And I will smile and laugh about that because, I've been working on this for a year and a half, and I know, yet I was very, very careful when designing these indexing operations to make really, really sure that I remain lazy and do not materialize anything at the beginning, which is why in this first pass I've stayed away, for example, from anything involving a colon operator to materialize an index sequence, because that would go through and could potentially be expensive. Hence this roundabout way of using selected ranges with matrices. But that's open to be revisited. And I would definitely appreciate a pair of eager and qualified eyes. So if you want to take a stab, the actual high-level R veneer that sits on top of the query functions is really not that much code, and we can probably put some other ones around it just as a test or as an experiment. So I'm open for stuff there. As for the dollar operator, that of course already works, because when you ask for a data frame, you get a data frame back. But so all the objects that you have once a query ran is an R object. So you have all the usual stuff there. Final part of that question about tidyverse, that also works. But it's a little tricky, and we've looked into this. So basically, we also like how the, say, DBI-based interfaces allow you to open a table object, pipe queries along, and then send the selection back. But if you look closely at what it does, say by ending your pipe in a collect call, you see a SQL statement. And in order to resolve that, you need a SQL engine, which we don't have natively. We're a storage engine, infinitely scalable, lots of things. We don't have a query engine within it, so we can't do that. However, we have an integration with MariaDB, which is a SQL engine with a query engine with pluggable storage. So TileDB can be plugged into MariaDB as a query, and then you can go from the tidyverse via DBI to our MariaDB, our MySQL, and send those queries. And I have examples for that in the user tutorial, and that just looks like any other dplyr query. It is, however, a little bit more difficult to productionalize, in the sense that you need, in your running code instance, a coherent build of MariaDB with the MariaDB extension, requiring basically MariaDB and TileDB to be built the same way. So we can't easily wrap that up for a download at CRAN, but it's really easy to deploy from a Docker container, as I showed there. And we're happy to show more of that in examples and have examples. So by all means, get in touch. We have that. And then the last question so far that I'm seeing in here from Bianca is, sure thing, we can, and already, because everything is our object, so you can lapply, sapply over them as you please. I have piped examples over query objects and things that come back. So that's why we're in R. So that's that definitely works. But again, the real reason why we're doing what we're doing is that you can potentially access data from a front end that sits somewhere very far away in the cloud at gargantuan size, gigabytes, petabytes, and you want to make sure that you're only getting the carefully chosen results back, because otherwise your laptop melts, and we don't want that. But if you just want to experiment with local data, you can also do that with just merely kilobyte, metabyte data sets on your machine. Experiment there. It works with that the same way.
Yeah, and I'll mention you could also use the DelayedArray integration to get access to their block apply family of functions, right? Or use the amazing delayed matrix stats package and get access to all of those delayed apply row sums, etc. Style computing. So that already works. I think there's some work we can do on our side to optimize things a bit. But if that's the style of computing you're used to, that already does work with the TileDB Array package and Bioconductor.
All right, I think we've reached the end of our time. If there's no more questions, I think we should all congratulate Dirk and Aaron on a really great talk.
Mark is attempting to phone in, probably to let us know that the session is over.
Am I muted?
Time. I think we hit all the questions.
I can hear you.
I think we've hit all the questions. Thanks, everybody.
You can.